All right, so this set of notes is going to talk about what is a metamorphic rock. It's obviously different than igneous or sedimentary. In this case, metamorphic rock, for the basis for understanding, is a rock that's been heated and put under pressure, but not melted. No melting occurred. If it was melting, it would go back to igneous. So, metamorphic rocks have been altered by heat and pressure. No melting. And there are different types of metamorphic rock. We have foliated, that is put in layers, so you can literally like flake them off in layers. Heat and pressure basically causes the minerals to reorient all in the same direction so that they get flaky. For example, foliated would be slate chalkboards, or slate at the bottom of a pool table. That is a metamorphic rock, and it's, you know, it's got nice layers to it. Schist is an alignment of flaky mineral called mica. Gneiss, Gneiss, is a bands of feldspar and quartz minerals. And a lot of people have granite in their kitchens. What they don't know is sometimes what they think is granite is actually a gneiss. So just to put this into understanding, I'm just going to give you a little precursor here. If you put enough, okay, so shale is a sedimentary rock, so just understand that. But if I take shale and put it under heat and pressure, it becomes slate. If I put slate under pressure, it becomes schist. And if I put schist under more heat and pressure, it becomes gneiss. It's a nice rock. So those are all foliated types, the slate, the schist, and the gneiss. Non-foliated metamorphic rocks are things like marble. There's no visible layers. It's kind of much more random. We can compress and compress and compress, and they just don't really, unless you get under super high heat, they just want to stay that way. So non-foliateds also tend to, like marble, tend to fizz because they're made with calcium carbonate. So here is that handy dandy rock chart, which I would highly recommend you write these two down in your notes, because you can use them on the test. Not going to have, normally I would make you be able to use these, and we do all these different labs, and we just don't have time because right now is, if you're watching this on here, we're not in my classroom, I can't hand out the rock samples, but I do expect that you can use the charts. So if I have a shale, that is a mud rock, that's the parent rock if we look up here. And if I put under low heat, it becomes slate. Under medium heat, it becomes schist. And under high heat and pressure, it becomes gneiss. Sandstone, interestingly enough, so sand that's parent is sand that is cemented together, which is again a sedimentary rock. Nothing happens to it. It's still just sandstone if I put under low heat temperature and low pressures. But the second I go to medium or high, it doesn't matter. It just goes to quartzite. So sandstone under medium or high heat or pressure becomes quartzite. Marble made out of shells is marble, or guess what? Marble. Doesn't matter how much heat or pressure I put on marble, it's still going to be marble. Granite, an igneous rock. If I put under low or medium temperatures and pressures, nothing's going to happen to it. But interestingly enough, granite, just like shale, when it's under high temperature and pressure, becomes a gneiss. And sometimes you can actually see in gneisses like these beautiful long veins as they've been pulled and pushed. It's kind of like you can take a rock and bend it like taffy, and you can compress it, and you can actually see waves in the rock. So rocks can actually be compressed. All right, so foliated, this is kind of that one to figure out what's what, like we do with the igneous rock. So how to identify? Here's the description, and first of all, it tells me if it's foliated or non-foliated. Always the first thing. If I see alignment of mud grains, it looks like chalk, I'd say that's slate. But if it's flaky material, that would be micas, like it looks like little pieces of glass, but kind of yellow, orangey yellow, that would be a schist. If I see bands of quartz and feldspar, and you're looking for stripes, definite stripes, like you'll see like white and black, and that's a gneiss. Marble, no visible layers, crystalline, and it fizzes with acid, it's marble. And if there is no foliation and it does not fizz at all, then that's quartzite. So really what we're talking about is metamorphic rock is they're heated and compressed deep underground because it gets warmer and warmer as you get towards the center of the earth. But they're near the molten material, but they haven't melted, and that's a huge indicator. Once it melts and rehardens, that's an igneous rock. Metamorphic rocks are just close to that heat source, And so they can get pushed down with the pressure of everything above it, and you've got the heat coming from the bottom, and it can get pressed and cold. You know, literally, if I take this scarf, I can bend it into layers. Well, that's what all the heat and pressure can do down just above the mantle. So these rocks are heated until they're kind of soft and squeezy. Think of it as like silly putty. You can take it and stretch it out, and then you can, layer it all, scrunch it back up and push it back together. But you're not melting it. You're just kind of making it into that softened state. So most metamorphic rocks form layers called foliation. And here you can actually see these are foliated rocks. These rocks have been compressed and heated, and they started to have alignments of their minerals. And they tell us the type of rock it is. I can go and tell you that has to be a metamorphic rock. It has to have been subjected to that heat and pressure, because I wouldn't see these layers unless that had happened. So think of it this way. Let's say I've got that mud shale thing happening. All my orientation of my minerals are going in every which direction. And as it gets buried deeper and deeper and deeper in the ground, the minerals start to kind of line up. And then they get a little bit out of whack, but you go far enough down, they actually all line up and they become foliated. This is just another kind of example. But the other thing I want to show you with this picture is, if you look here, you can have compression. In other words, we can squeeze in multiple different directions, but you can also pull. And if I'm under pressure pushing together, that's called compression. And if I pull them apart, that's called tension. So we have lots of different things. And this is just, again, showing you pressure, the original material. It can be squeezed and compressed, and it will start to line up your minerals into oriented patterns. So slate, very fine grain, looks like chalkboard, because that's what we used to make chalkboards out of, formed from mud that has been under heat and pressure. We use them in pool tables and on chalkboards. And it can be different colors, but you see the nice layers there. You can definitely see some layers where it would crack off, which is why we can use it for like chalkboards and pool tables, because it's a really solid surface, but it breaks flat, so you get nice clean surfaces. Schist, this is, you see how it's kind of sparkly here, and it's starting to orient. So we took that slate and we applied medium heat and medium pressure, and it's starting to make that mineral of mica flow out and kind of form in nice sheets, and it starts to become just a little shiny, or really shiny, depending on how much mica you have. If I put it under, okay, so slate, schist, nice, or granite can also go to nice. And these are layers, and look, you can tell this is metamorphic because look at this nice, it started to form layers, and you can see banding in here, right? You can see banding down in this bottom one. But look at how this curves down and up. And that's, if we were in class and I had my rocks out, you'd actually call this the syncline. You slide down the syncline, and where it goes up and looks like the top of an A, that's called the anticline. That's what those folds actually have a name. So that we're in the field, we can say, oh, this is the syncline, and that would be the anticline, if that's the direction the rock was found. It's really important to understand where a rock comes from, because that tells you a lot. If I find a rock in a riverbed, it could have been from Canada. It could have been from next door. The glacier is really good at kind of mixing up our terrain. So a lot of rocks that we have in Minnesota actually came from the Canadian Shield, because the glacier pushed all that stuff down here, and when it melted, it dropped it. We actually live on something called glacial till. So if you're looking for bands where you're really seeing oriented grains, darker and lighter, or these kind of compressed patterns, now you really know you're looking at a nice. Non-foliated, no layers or flakes or visible bands, and it can be still under heat and pressure, and it fizzes with acid. You're looking at a marble, because it doesn't matter high heat, low heat, medium heat, you get a marble. And I like this because look at the anticlines, the up moves, and then down to the synclines. Here is, if you're trying to figure this out, this is a piece of slate. You can see nice layers going on in there. Okay, if I told you that this has no foliation on the left, but it does not fizz with acid, we would know it would have to be quartzite and not marble. So those are just some of the quick things we've gone through in the notes. I would highly recommend that you go and copy down the Metamorphic rock table. Again, those tables you can use on your test when you get to structural geology A test, or rocks and minerals test, depending on which year we are doing this. And the next thing you need to do is check off in Edpuzzle. These notes are available at the bottom of the page if you want to go back and look at it to copy those charts down. Otherwise, you can go back and pause the video. But that table's there for you to copy down. As always, if you need help, let me know.